College's Industrial Process Control. This video is Lab 5, PID Control. After completing this lab, you should be able to describe the actions of a proportional integral controller as it relates to a filling operation, explain the purpose of using an open loop response while setting up the PI operation, create an as-found condition, and use a filling station to tune a PI controller during operations. This lab consists of 3 parts. Part 1 will be setting up the proportional integral controller using an open loop response. Part 2 is creating an as-found condition, and Part 3 is tuning the PI control while in process. The first step will be to gather the materials and set the equipment up. You will need the following pieces of equipment. You'll need 1 pressure transmitter. You'll be using the trainer station's Brian brush control box. You'll be using the trainer station's pump and tank unit, complete with its process lines. You'll need the trainer station's column receiver tank. You'll need 3 impulse lines and 1 10-mA current calibrator. With this lab, the only device that requires mounting will be the pressure transmitter. Once you have gathered all the material, you can begin by connecting the process lines. You will use the existing supply and return process lines that are integrated on the pump tank unit. They will both be connected to the bottom 2 inlet ports on the column receiver tank. Be sure to put the supply process line on the right, non-glass tube side of the receiver tank. You will connect the high pressure impulse line from the transmitter to the bottom of the receiver tank. Connect the low pressure impulse line from the transmitter to the top of the column receiver tank. Use the 3rd impulse line to purge any air or water from the transmitter. The next step is to make electrical connections. With this lab, there will be 2 different wiring configurations. The first will be for the open loop response, whereby only the current calibrator will be connected to the PI controller. The second will be for the running process, and the PI controller will be connected to the pump and the pressure transmitter. Let's begin with part 1, open loop response. The 10-mA calibrator will be used to emulate a current signal being sent to the PI controller. The system will react as if this device is a pressure transmitter and will send out a response. However, the output side of the controller will not be connected. The 10-mA will be connected to the controller through the connection ports on the side of the Brian brush control box. Make sure its range is set from 0 to 99 milliamps. Leave the unit off until you're ready to begin. It will drain the batteries quickly otherwise. As demonstrated here, the wiring is very simple. The 2 leads from the 10-mA go directly to the Brian brush box's current input number 3 and common number 3. And an additional jumper connects the current input number 3 to voltage in number 3. No other wiring is needed at this point because the controller is being set up for open loop response. The next step in the process is to begin working with the Brian brush HMI. Turn on the Brian brush box, and then set the reverse direct mode selector switch to reverse mode. When the HMI finishes startup, the opening screen will appear. Use the tactile response screen and press the continue push button. The next screen should be the select a control screen. On this screen, find the level flow push button and press it. The select a process screen will appear. Find and select PID level. The PID level screen provides a visual representation of the system. The silver cylinder on the left represents the holding tank, while the square open tank in the center represents the column receiver tank. On the right side of the screen, is all of the process information we need to know. There is a column of 4 display push buttons. The top one is the set point, which will show the desired set point of the process variable. The one below it is the percentage of process variable. This is the current value of the process variable as seen by the controller. The process error display button reveals the difference between the set point and the process variable. On the bottom is the manipulated or control variable. This is the amount of water entering the receiver tank. You can now turn on the calibrator. The screen will now show the system in its current status. This is similar to a technician station in a control room. Remember that this control room could be located kilometers away from the process. Therefore, it is critical that the system is calibrated properly so that the screen is a true representation of the system's condition.
In this lab, we're looking at the attributes of a PID level control. Right now what we're doing is investigating the open loop response, and by doing that what we have to do is take out the final control element so it does not adjust the process. But what we do have is the control connected up to a calibrator where we can inject the signal, and we're faking, basically what we're doing is we're imitating or faking what would come from the transmitter that we have in this case. Right now I have a set point of 50%, a process variable of 25. If you subtract 25 from 50, what you end up with is a 25. If I reduce or increase the process variable, what you see is that as I'm increasing the process variable, the error is decreasing. The error is simply set point minus process variable. Now what I do is I have a process variable of 40%, so the difference between them is 10%. What I'm going to do now is I'm going to enter gain. Now with gain, the greater the number, the more output you have for any given error. I'm going to enter a simple gain of 2.
While working with the HMI, you will often find it necessary to enter data like a new set point value. To do this, press the Set Point Value Display push button. A number pad should appear. Press the numbers required to make the new set point, for example, 5 and 0. Then press Enter. The keypad should disappear, and the set point should now be visible in the display push button. To access system parameters, you will need to find the Technician submenu. Press the Technician display push button. A pop-up menu should appear. The submenu has 3 choices: tuning, where proportional, integral, and derivative gains can be entered; alarm points, which allow you to set different process variable points to trigger an alarm state; and close, to exit the pop-up menu. To program the gains we require, we will need the tuning menu. So press the tuning display push button. A pop-up menu should appear. Here, we are given 3 choices: gain, integral, and derivative. The gain push button gives access to the proportional gain setting. Since all PID controllers begin with proportional component, using the term gain alone is perfectly justified. Notice it can be set to any number from 0 to 20.0. The integral parameter has no decimal place because its parameter is a period of time, the reset. The integral gain used is the same as the proportional gain used by the controller, so the controller only needs to know the x value, or the time, to determine the ramp. The derivative push button sets the derivative gain used by the controller. This lab will not include the derivative gain setting because the current controller does not have this feature. Also, recall that derivative gain has 2 possible base values, that is to say, two things it can be based on. And this can cause an enormous amount of swing. Only adjust this value under direct supervision and careful instruction. The next step is to actually add the gain that you wish. Press the gain display push button. Again, the number pad should appear. Use the number keys to enter the values shown on the process sheet, and then press enter. Repeat the process for the integral when instructed to do so. Then, use the close push button to remove the pop-up submenu from view. At this point, the controller should be using the gains that you have entered.
So I go into tuning, I enter a gain of 2, enter, and what you see here, which is the output of my controller, I have 50% set point, I have 40% process variable, and I have a 10% error, but the gain of 2, so 2 times 10% error, gives us a 20% manipulated variable output. Now, I'm going to reduce the process variable. I bring it down to 30. 30, there we go, 30. And what I have is an error of 20% times 2 gives us 40%. Now you'll notice that this control rounds the numbers. So if it's reading 39.5, it'll actually just show up as a 39. So what I'm going to do is change. I'm going to change my set point. I bring it down. I'm going to bring it down to 30 now. Oop. 30, enter. And what you see here is I have a 0 output of my manipulated variable. What I'm going to do is just go back to changing this to 50% and just show you what happens if I enter in a higher gain. Watch the manipulated variable. I'm going to enter in a gain of 4. Enter. And what you see is the output, the manipulated variable, percent manipulated variable, is the output of my controller going to my final element, is increased significantly. It's gone up here to, well, showing 79%, which is close enough. 80% should be 4 times 20, 80% output. Now, what happens in a process is we'll have what's called steady state error. After the proportional has done its job, there is still a little bit of error left, and this error exists over a long period of time. So what we need to do is add in integral. The integral is actually a measure of seconds, and it's the number of resets or repeats per second. So if we enter in 10 seconds, it means that there's 10 seconds for every reset or repeat. It will actually add that portion of the proportional to the output of the controller, and in fact doubling it over that period of time. So I'm going to change my gain down to a 2. I'm going to increase my process variable here a little bit to 40%, giving me an output of 20%. I'm going to enter an integral of 10. That means in 10 seconds, the output of the controller is going to go from 20% to 40%, 20 plus 20. So I go into integral and I enter a 10. As soon as I hit enter, I start counting. 1001, 1002, 1003, 1004, 1005, 1006, 1007, 1008, 1009, 1010. I'm a little bit slow there. We actually got up to 41%. Here, it's continuously climbing. I'm going to change that integral to 0 just so I can reset it. And now I'm going to enter an interval of 20 seconds. That means in 20 seconds it will double. So I hit enter, 1001, 1002, 1003, 1004, 1005, 1006, 2007, 2008, 2009, 2010, 2011, 2012, 2013, 2014, 2015, 2016, 2017, 2018, 2019, 2020. Again, my count's probably a little off here. I'm not really using the clock. It's kind of hard to show here with the setup we've got here. But as you can see, the manipulated variable on the screen here is increasing. It is actually still climbing, and it will continue to climb until it gets up to 100%. It's basically adding to the output of this controller until that steady state error disappears. If I increase the output of my calibrator and get it up to 50%, you'll see that the manipulated variable no longer increases. If I go over and above, you'll actually see the output actually now reducing, because now I'm over the set point. I actually have a negative error. It's subtracting that from the output of the controller. Now what I'm going to do, put this back into, so I got 0 error. I'm going to change the integral to a 5, and what you'll see is that when I enter a lower number, what I have is a process or a control that reacts rather quickly, whereas when I had the higher number, the control was more subtle. It actually slowly gained to the gain the output of the controller itself. So I set this back to 0. I'm going to put in a integral of 5. As soon as I hit enter, 1000. I have no error. No error. I get no output of the controller. So I'm going to clear this. Hit enter. I'm going to give it an error of 10. So that gives me a 20% manipulated variable output. This should go to 40 in 5 seconds. So I'm going to enter 5. Hit enter. 1001, 1002, 1003, 1004, 1005. Maybe I'm a little fast this time. But as you can see, what it's done is just adds to that. And it does it by, you enter the value in seconds per repeat. And what happens is it just continues to add on. It gets up to a value of 100% and stops. That's as high as the output of the controller will go. We have it set for 100%. So that's really the actions of PID control. What we're going to do is investigate how this pertains to the process itself by going live. We're going to go from an open loop response to an actual control. Okay.